part 4. We have done we understand superposition is important. We know what is entanglement, and we know measurement is important, right? That they are so profound, I cannot get all the information. And we see that if we are smart enough, come up with algorithm like Deutsch, you can get the function whether it's constant or balanced by sacrificing other information. We need, but however, you need to be able to incorporate the function you are interested in a quantum oracle, right? And of course, you know how to write a simulator in Colab. You know how to use IBM-Q. I did it very fast. I hope you can watch the video again if if you are interested later. Now let's go to the hardware part. How will we, what is the limitation of hardware and how we will realize what we have discussed in hardware? Here very quickly, let me just skip this. No, I want to say something. If you're an electrical engineer, I always think that electrical engineer play an important part in quantum computing, right? If you know semiconductor, you know that the physics people, they developed a very complicated band theory, golden Fermi rule, Bloch function, to study how an electron scatters in a transistor. Very complicated. This is more complicated than quantum computing, actually. But the engineer come up with an empirical equation, and they sell this product, and this is a 100 million market. We call it TCAT in semiconductor technology, computer-aided automation. Same in quantum computing hardware. We have this like J's coming Hamiltonian. You need to solve them, and of course, this is already simplified. There are many other things. If you can come up with an analytical equation, again, right, you earn the money, not the physicists. So you should think about this. And there are lots of room that you can do in a quantum computer. Here I show you a typical superconducting quantum computer. Here is controlling, let's start with this qubit chip. This is a chip on which you have 1 qubit Josephson junction, maybe tens of micron. Even this chip itself is just traditional semiconductor fabrication. All these are the so-called resonator. All the electrical engineer have been studying for a long time. It's cooled down at 10 millikelvin. How we control it? As we said, a quantum computer is just a passive wave function sitting there. And we shoot the microwave pulse, laser pulse to it to manipulate it, to rotate it. That is a quantum gate. And we do it right, then we get the answer we want. How do we do that pulse? You need to have a programming interface, and then you ask it to generate the pulse shape that you want. Then you bring it up to a high frequency so it can transmit as a microwave all the way to here. You need a so-called circulator to direct the signal to the right place so that it won't reflect back. You need some amplifier to get the signal. So all these are classical. You start from room temperature, but at the end, you need to cool it down to 10 millikelvin. So this, again, mechanical engineering or like all those guys do that. Cryogenic electronics, how do you design low temperature, high electron mobility transistors, right? So only two things is really quantum here. One is this Josephson junction, which is just aluminum oxide, and aluminum. That's it. Another is this so-called parametric amplifier. Parametric amplifier is a quantum amplifier that it add the least noise to it. When you amplify something, you actually add more noise to it. There's something called noise figure. So, which is not good. So do not think that more amplifier is better. The signal to noise ratio will get less and less. Okay, so these two are real quantum. Other than that, everything is classical. Okay, so that's a quick overview, right? To make a quantum computer, divisional has 5 criteria. First, you need to be able to keep it with 2 energy levels. Just now she asked about ground. Does it need to be the ground state? No, or the basis state can be lower energy and high energy state. But you need to make it within this 2 level. You cannot, let's say, ground and exciter level. You don't want to bring it to the 3rd level, because once you goes to the third level, you are not in the Hilbert space 0 and 1 anymore. You are not a qubit anymore because you have 3 basis states. So your system should be able to have a well-defined 2-level, right? Second is initialization. Remember, we just say in Deutsch algorithm or all the algorithm I show you, we start with 0. Now, it's very often some quantum algorithm need to keep initializing the circuits after the measurement. If you take you 1 second to initialize, then it's useless again because you might need 1 trillion initialization. Then that is useless, right? So you want to be able to initialize that very quickly. Usually there are 2 ways. One, just let it thermally decay from the excited state. That takes a long time. Another is so-called active reset. You measure it, you see that it is at high state, then you apply a NOT gate to bring it to the ground state. And if it is at ground state, you do nothing. That's so-called active reset. That is much faster, okay? Another is so-called coherence time. We will talk about more later. But basically, this is, it's noise. How can I keep it at that state? I need to keep it long enough so that I can apply enough microwave pulse to operate on it so I get the answer before it deteriorates, right? So long coherence time. You also need to have a universal set of quantum gates. Just like in CMOS, we usually say you need to have layman gates. If you have layman gates, you can create any circuit you want. Here, it's not really any circuits, but in principle, you cannot have a universal set because your space is so large. But as long as you have certain 1 qubit gates and an entanglement gate, which I mentioned earlier, like the C0 gate or a swap gate, then you basically can do most of the important stuff, okay? And you won't take this, you usually take this for granted. You should be able to measure the qubit specifically. At this time, I only want to measure this qubit, not the whole system, because I don't want the whole system to collapse. One very simple example is just like the error correction, right? Remember, we have this ancillary bit. We only want to measure the ancillary bit. If you come up with a new hardware, which is very great in every aspect, but whenever you measure, you need to measure all of the qubit at the same time. Then you don't have error correction. Then that system die already. Okay. There are more criteria for quantum communication we can skip here. Right. So how do we implement the qubit? We can use electron spin. Right. We have a well, and then under magnetic field, spin up and spin down, we have different energy. Right. So I can have a state which is a linear combination of the spin, right? So now here we go back to how we implement the 0 and 1. And we try to limit ourselves only at the 0 and 1 state. So we use spin down to be 0, spin up to be 1. And it can be a superposition between these 2 states. Again, if I don't measure it, I don't know where it is. Or photonics, this is something interesting also. They are connected, so so maybe you have something like this. You have photon, only 1 photon coming in. And if they're symmetric, then they have equal probability to go to path 1 and path 2, right? From a wave perspective. So whether is it in path 1 or path 2, I don't know. It's a superposition between them. But it's only 1 photon. If I measure it, for example, I put a Geiger counter here, and I find that it's on path 1, then the wave function collapses. The photon is in path 1, definitely not in path 2, because I only have 1 photon, right? So this represents the measurement. What we are talking about today is the superconducting qubit. There's something called Josephson junction. We will talk about that later. But Josephson junction is nothing but actually is just like a capacitor. So this is like a capacitor. So we have an island here. So we cool for a superconductor, all the electrons will pair up. Probably you know already. Becomes something called Cooper pair. Electron and fermion, right? We learn in chemistry. They cannot occupy the same state, right? In hydrogen, if I have 1s, this spin up, then the other must be 1s spin down. I cannot say I want to fill more 1s. No, I need to go to 2s, right? Because they're fermion, they have spin half. But when you pair up 2 electrons, it becomes a boson, so-called like the night photon. because now they become integral spin. So they can occupy the same state, and they prefer to occupy at the same state. So think about what is laser. Laser is that you have a lot of photons with the same state. They have the same phase, same direction, same polarization. So it's like a group of army marching together. That's why the laser is so strong. Now, if you make electron become a Qubit pair at super low temperature, then they all occupy the same state, ground state, and they have the same phase. Everything is the same. It becomes a mesoscopic object, quantum object. It's in the order of micron. You can see the quantum behavior even at the micron level. You don't need to go to nanometer or angstrom, right? So try to think about this. And how do we store a qubit? This island can have 0 or 1 extra Qubit pair. So it's not very difficult to understand. You just think about, this is just an island, right? I have capacitor. I put 1 more Qubit pair. It means 1 pair of electron. Or I don't put 1 more Qubit pair. So as it is, or I have 1 more. And that creates a superposition. These two are the basis state, right? Basically, just like that, do we have 1 more audience here, or we don't have 1 more audience? That is 2 basis states, and the state can be a superposition of this. Is that okay? Okay. Now, and based on this, you see that the main point is that you need to be able to separate these 2 levels very well. If they are very close to each other, if they are noise, you cannot separate. Like this building, we are on, I don't know, 2nd floor. How do you know it's 2nd floor? If let's say we are actually on a ship, this ship is vibrating by 2/4 of amplitude every second, right? Then I really don't know whether I'm on the 2nd or 3rd floor, because just the noise itself is larger than the separation between 2nd floor and the 1st floor. And same for this state. They say a ground state and the high and 1 state. If the thermal noise is so large, right, it can hurt the states, and also it becomes, we have so-called energy broadening, right? You cannot define the state very clearly. But anyway, the message is this: the qubit will lose the state due to noise, so we need ultra low temperature. We either use dilution refrigerator or use laser cooling in trapped ion case, right? Here it shows the energy scale as a function of temperature. If you are at the room temperature, 300 Kelvin, your energy scale is about 26 millieV. I think you guys know that, right? And if you cool to liquid helium, which is 4 Kelvin, it's still at 0.34 EV. But the qubit energy separation is 0.02 EV. So usually the qubit, here is actually about the superconducting qubit, but most of them are the same, cannot operate at 4 Kelvin because your thermal energy is so large already. That's why we need the dilution refrigerator, which is about 50 times smaller than the energy separation of your qubit to have the quantum computing working. Okay? Otherwise, there will be decoherence. What does it mean? There are two types of them. Usually we characterize in 2 ways. One is called T1. T1 is talking about I prepare them at the high state, and then it will start decay, right? This is probability. This is statistics. Some of them just stay forever, right? But as the time goes by, most of them will decay. Here is a statistical result. When you just start, 100% are at the 1 state. Then as time goes by, you will keep decaying. And if this is a log scale, so you can fit this line with an exponential curve. In this, like exponential negative t divided by t1. As the time, when time is 0, this is 1, so all of them are at 1 state. But when the t increase, this becomes smaller and smaller. And this fitting parameter t1 is the t1 time. In this case, it's about 200 microseconds. Then what it means if you want your qubit to be useful, your gates time, you apply a NOT gate, Hadamard gate, or whatever gate, maybe need to be less than 20 microseconds or even a few microseconds so that you will be able to apply the operation. Another is DT2, is dephasing. If you are in the superposition, right? You may still be in superposition of 0, 1, but you don't know whether it's still 0 plus 1, 0 minus 1, 0 plus I1, or 0 minus I1, or all other possible combination. The phase relationship got lost. But why do I care about phase? Think about the quantum Fourier transform, the matrix. It's all complex number, right? So if we want to do interference, you lose the phase information, then you cannot do interference again anymore. If we look at this, for example, the reason that I have constructive interference when I multiply the quantum Fourier transform is because the first 9 are all the same, positive. If I lose phase information, this guy may become negative 0.354. Then it becomes destructive interference. Then my program will fail, right? So that's why it's important to preserve both the T1 and T2 time. And T2 time usually is smaller than T1. In this case, it is too small. Yeah, it's bad, 19 microseconds. So now you know that your gate time better than less than 1 microsecond for each gate. Okay. Yeah.
Why do you say T1 is 219?
Why? Because it fits this equation. The equation is exponential negative t divided by T1. So this is the constant. So it means it's an exponential decay. It means when you reach 219 seconds, you reduce to about 3.6 something, e to the power negative 1. Yeah, that is the definition. Yeah. Okay, so let's talk about superconducting qubit. We talked about Josephson junction, right? Actually, it turned out that you can make a quantum computing or quantum theory very easily. Just use an LC oscillator. We won't go into details, but the problem is that in an LC oscillator, just an tank, if you go to very low temperature, you can it only has discretized energy level. You can store 0 photon. By the way, you will see that people talk about photon when they're talking about the microwave circuit, which makes sense. Remember, photon is just electromagnetic wave, right? The light you're seeing just electromagnetic wave. They are the same as your EM wave on the circuit, but it's just a photon you cannot see now. They have much lower frequency in the gigahertz range instead of terahertz or higher range that we usually talk about. LC10 has equally spaced 0, 1, 2, 3. Do you still remember how we do the NOT gate? We say that we apply a pulse to it, right? Every gate is a pulse. If I apply a NOT gate to 0, it will bring it to 1 because the energy match. If I apply another NOT gate, I hope that you will go to 0. But however, if the spacing between 1 and 2 is the same, it may bring the state to 2. And in that case, your quantum computer doesn't work because you are excited to another space, no longer the 2-level Hilbert space you are looking at. So that's why you cannot use LC10. And that's why people come up with Josephson junction. The Josephson junction has a similar portfolio, but the distance between different levels is not constant. This is the ground state. We can call it 0. This first excited state, we can call it 1. Good. Apply a pulse to it, then it will go from G to E, from 0 to 1, and then apply a NOT gate to it, it will go from E to G. You keep recycling. Can it go to F? No, because the distance here to F is shorter, smaller than the pulse I apply. So in quantum mechanics, right, you need to match the energy in order to go from one state to another state. So this is the key word you hear a lot is the anharmonicity. This is not harmonic, purely harmonic. So the distance is not the same. So that's why Josephson junction is a good qubit in this sense, because we can confine it in the 0 and 1 state. Okay. Here is just some more information about Josephson junction. You have a superconducting aluminum, and then on the left and right, and then you have an insulator. So again, that's why I said this is nothing but just a capacitor, but it's a capacitor with a superconducting metal, right? You also don't need to know this. The only thing I will show here is to show you that the effective inductance here is non-linear. It's not a constant. It changed with something called phase. We won't go into details. And because this is non-linear, that's why you get this this enharmonicity. You have different spacing, right? This is the only thing you need to know about their non-linear inductance for Josephson junction. Let's see, okay. So let's go back to the system. So what does a quantum computer look like? As I said, here you have a lot of FPGA, right? Looks like I'm advertising for this company, but that is indeed the one we use. Quantum machines, they're also sponsor for this conference. You send your Python program to them, and then they will just generate the correct pulse. And then you go through something called mixer to bring this pulse to high frequency. You have attenuator. This is to attenuate the noise from the room temperature. The room temperature has a lot of noise, thermal noise. You want to attenuate them, right? Then at the same time, the signal got attenuated also. That's why you need to start with a large signal. Then when you reach here, the noise attenuated to a level that is less than the quantum noise. So they have no effect. And then your signal is still large enough. Then this signal will go to here through this chip, right? These are the transmission line. And then it has a qubit here based on this paper, right? This is just microlithography, like what you see in semiconductor. This is the Josephson junction, very tiny. It has a metal and then another metal overlay isolated by aluminum oxide. You cannot see it. Here are two big capacitors. So this is another type of qubit. We call it transmon, which you will see a lot also, right? Google and IBM use them or their variation. Basically, it is a Josephson junction, just a Josephson junction, shunted or in parallel with a huge capacitor. This is to reduce the sensitivity to charge noise. Right? We don't need to go into detail, but that's just say why you have a big capacitor here is because we want to make a transmon. The microwave pulse go into here, and then it will be and then it will do something, either rotate the qubit, or when you are reading, it will be reflected back. And then we'll go through an amplifier. Here is so-called traveling wave parametric amplifier. It's a quantum amplifier. Remember, I said that when you add an amplifier, you will add noise to it because amplifier itself generates a lot of noise, right? That's the overhead. This one add the minimal noise to it. So that's why we want to start with a quantum amplifier to amplify it to have a large enough signal before we go to a classical amplifier. And then you read the signal. Based on the signal, you determine the state, which I will talk about that a little bit more later. Okay, here is, we can just quickly go through this. The only thing I want to say, if you learn from microwave engineering, the first stage is very important in terms of noise. You want to add the minimum noise at the first stage because all the noise will be suppressed. All the noise in the later stage will be suppressed by the gain. So you can add more noise at the later stage. But the first stage, you want to have the minimal noise. So it's okay to have less gain, but minimal noise. So that's why we use this quantum amplifier, right? Quantum amplifier is not, what people do is a parametric amplifier. You can imagine it is like this. You have a capacitor. When you are at the high voltage, you try to pull them apart. And because they are at high voltage, you pull them apart, you actually reduce the capacitance. And because you reduce the capacitance, then you will be able to add more charge to it. No, you will be able to add energy to it because the charge there are the same. They don't change immediately. Then you will add energy. So where does this energy come from? It comes from the fact that you are pulling it. You are doing work to this capacitor. And then when it is at the cycle that you don't have electric field across it, you just put it back to the original size. And because you don't have charge, you are not extracting any energy from it. The only you need some time to really go over this, but message is that you try to apply external excitation at a frequency, and the phase that is correct, so that your excitation keep adding energy to it. Just like the swing, right? When you do the swing, how do you swing higher and low, higher and higher? Is that you do the correct excitation at the right place. Then you will start swing higher and higher. This is like the parametric amplifier. This is the only message I want to say. And that is how it works in a quantum traveling wave parametric amplifier. So you do need to have a pump frequency so that it will amplify your signal like what we are talking about earlier. Okay. There's too much, but that's okay. And here I just want to say, I usually show the student, come on, this is exactly what you learn in device physics and microwave engineering. Just do a ham design, right? And you put in the LNA. That's why electrical engineers should really go to the quantum computing, right? This is just a typical noise amplifier, ham an amplifier. Now here I want to go a little bit into the details so you understand how it's related to the gate. So when we generate the signal, we will generate the so-called IQ part, the in-phase and quadrature part. Because if I want to have a signal, right, I want to apply this signal to it. If I just go through the math, this is the carrying frequency. If let's say this is the signal I want to apply to the qubit to do a NOT operation, right? You just go through the physics, you find out that to do the oscillation, maybe I need to apply a pulse like this, right? You go through the physics. And then what I can do is I will just take this high frequency part away, and then I put in the I part, which contain the amplitude and the phase information. Amplitude and phase are very important because they determine how your qubit evolve. So from this classical control or pretty low frequency megahertz, 100 megahertz regime, we generate the I and Q signal. And then we have a carrier, for example, 7.2 gigahertz, to mix it so that we bring it to a higher frequency. And this is sent to the qubit to do the manipulation. Since we do not have chance to go to the physics, as this is an introductory class, and again, you can look at my the video I showed earlier about the quantum computing architecture, where we will discuss this Hamiltonian. But here, I just want to tell you that how the qubit change, it really depends on the frequency of the qubit and the microwave frequency, and also the amplitude of the pulse you send, and also the initial phase of your signal, right? So afterwards, I just want to say that you change the qubit by changing the phase of this pulse, by changing the amplitude of this pulse, and also by changing the frequency of this pulse. Then you will enter to this equation of motion for the qubit. And here, you probably don't know, but here determine how it rotates about the z-axis in the Broad sphere, how it rotates about the x-axis in the Broad sphere, and y, right? So I set the phi, the omega correctly by changing the phi, a, and also the frequency. I will be able to rotate it about the Broad sphere to any point. And as I told you earlier, a Broad sphere is nothing but just mapping to the space of the qubit, right? So if I can rotate to any point on the Bloch sphere, it means I can do any operation in the space. Then I realize my qubit, 1 qubit gate. Okay. Now I want to talk about how you read a qubit. I will skip this slide. The way you read a qubit in superconducting qubit is that you have this qubit here is coupled with a resonator. This is a microstrip resonator. It's a resonator. Okay. Now for a resonator, it's like this. It has a resonance frequency. So for a certain frequency, which is not at the resonant frequency, you will get transmitter because it resonates. If you're not at that frequency, you will get reflector, right? So we call this S1 matrix. When you have a qubit there, it would change the resonance frequency by this amount. If your qubit is at 0 state, and actually this label is wrong actually. If your qubit is at, but let's just treat it. It actually should be swapped. Your qubit, let's say in this case, your qubit is at 1 state, you will increase the resonance frequency. If your qubit is 0 state, you will reduce the resonance frequency. Why is that? It's easy to understand because now you have a whole system. You are not just having the resonator itself, right? It's just like if I carry my son, if he's heavy, then of course I will jump slower, right? If he's light, then I will jump higher, right? Because we're coupled, right? So this is just the same. Although there's a field, that's why I have this line. This is completely based on the cavity atom interaction. The physics people already done that before. They found that this shift of the frequency we're addressing, right? So they call this cavity quantum electrodynamic, and that's why in superconducting qubit we call it circuit quantum electrodynamic, because this qubit behaves as an artificial atom. Now that is the good thing about superconducting qubit. Almost all other superconducting platform, they use natural atom or natural quantity, spin, right, trapped ion, photonic, right? All this, they are natural. We cannot tweak those parameters. But if we use a artificial atom, we can really change a lot, change the coupling by just changing the layout. So the design space is much larger. And that's why it's good about this. Of course, the bad thing is variation, right? Because hydrogen is hydrogen everywhere. But if I want to make this same qubit for transmon, it can have variation even on the same chip, right? That is one issue. But anyway, the message here I want you to get is that we treat the superconducting qubit like the cavity at interaction with atom. So the qubit is like atom, and then we have this resonator, and that's how we read it. The change of frequency, we call it cross curve, okay? We say that the cavity resonance frequency is pulled by the qubit. And that is all you need to know, although there's some equation, you can read them if you're interested, right? And because of this, like we look back at this system, we shoot a pulse to this, and then let it reflect, okay? And so depends on the reflection, because at different frequency, you have, because if the qubit are at different states, you are going to have different resonance frequency. So all I need to do is just measure at the middle. Why? Because all this reflection, they have real and imaginary parts. If we shoot the microwave pulse out of the resonance, the real part may be like the real part will be this as a function of frequency. And the imaginary part will be this as a function of frequency, right? So if I have two possible situations, one is that I have the qubit at 0 state. It might shift to here. And then if I have a qubit at 1 state, it will shift to other parts because its resonant frequency is changing by this cross curve. Now, if I measure here, you clearly see that if it is shifted to the left, the imaginary part is negative, right? Because this blue one is the imaginary part when it is shifted to the left. Sorry, it is the real part. Blue is the real part. But if it's shifted to the right, the real part is positive. Right? So I just need to measure the real part. Then I know that whether it is shift to the left or shift to the right, the resonance frequency. Whether the resonance frequency is shift to the left or shift to the right. But then it's shifted based on the state of the qubit. If the state of the qubit is 0, maybe it shift to the right. If it is 1, it shift to the left. Then by measuring the real part, I know that how it is shift. So I know that whether it's 0 or 1. That is how you measure superconducting qubit, usually. Make sense? Thank you for answering me. So, but however, the point is that we have noise. So if you try to plot the imaginary part and real part with some transformation, you don't see only 2 points, right? This figure clearly shows that you can only have 2 points, shift to left or right. But because of noise, like here, when you measure it, you actually come up with a block, right? We call it IQ block. And you want to make them to have enough separation so that you can distinguish them. So this is after calibration, then you do a measurement. If the measurement fall on top of this, then we say this is 1. If it's fall below, then we say it is 0. That is how you distinguish 0 and 1. Yeah.
Real and imaginary part.
Yeah. So-called real, it is not, is that we shoot a microwave pulse to it, so it has phase with it, right? So if you have a phase, you can always write it as A e to the power I phi, something like that. So with this, you also can convert it to alpha plus I beta, right? Because so the so-called real imaginary is just that you get the phase, you get the amplitude, then you just convert to the real and imaginary part. It's just a post-processing. You measure voltage, but also the time it arrives, the phase. Yeah, good point. Yeah, you don't have imaginary voltage. You're right, yeah. And here is after some further transformation, but they are equivalent. Okay. Yeah, that is, maybe I will skip this one. Now, so let me go back a little bit again, how the do a single qubit gate, right? Let's just summarize. Again, we say that every state of your qubit can be mapped to the Bloch sphere. Again, this Bloch sphere is something you embed in the 3D space we live in, but it is not our 3D space, okay? Every point corresponds to the qubit space we cannot see. But we map it to here because turn out the math is very useful, very interesting, and it correlates to the magnetic field we apply. So we can think of this as when you apply a gate, all you are doing is just rotate the qubit on the surface of the sphere. That's it, right? For example, you rotate from north pole to south pole, you did a log gate operation, south to north, another north gate operation. You can also rotate from here to here, then it's a Hadamard gate because you become a superposition of 0 and 1, right? And you can do anything. In general, you can write it as equation like that, not very important. But here I do want to say one thing. Then how about for superconducting qubit? It turns out that you also can map this. Remember, we're talking about 0 and 1 extra Cooper pair as the basis state. We're asking, do I have 0 or 1 extra Cooper pair? Or a superposition of it, half of the chance I have 0 and half of the chance I have 1 for that particular state. We are talking about quantum mechanics, right? So it turned out that we have some energy, which is Josephson junction energy. We talked about that earlier. We have Josephson junction. We did not talk about energy, but we talked about the inductance, right? And naturally, you will also be able to store energy because it's an inductor, although it's a non-linear inductor. right? And then you also have another energy, which is the charging energy. This is just physics, you can ignore it. But the main point is that it turns out that you can map this problem equivalent to a spin problem with an external magnetic field. We are not saying that there's a magnetic field. We are just saying the way that is evolving is the same as I have a magnetic field there, and the magnetic field is given by the inductance energy and charging energy if you map to the broad sphere. Again, this is not a real magnetic field. We try to map the physical problem to there, right? And why I want to say this, the point is this, now a broad sphere, you go through the math, you find that the Hamiltonian, which governs the equation of motion, depends on delta, which is the frequency you shoot in, and also the charging energy and Josephson junction energy, right? And this determines how it rotates about the z-axis. And here, the phase determine phase and also the magnitude determine how it rotates about the x and y axis. So by doing which I already mentioned earlier, by changing the frequency, changing your Josephson junction design, the charging energy, Josephson junction energy, change the phase of your pulse, change the frequency of your pulse, change the amplitude of your pulse, you will be able to rotate it to any place on the broad sphere, which is just a quantum gate, because a quantum gate is a microwave pulse to rotate it about the on the broad sphere, corresponding broad sphere. Okay, here is showing an example of a NOT gate, and finally, here shows the example of swap gates. That if you want to have a 2-qubit operation, most importantly for entanglement operation, we use something called I-swap gate. Not exactly the same as the swap gate we skipped earlier. It has an I in front of it, but you see that it has off-diagonal term, right? Basically, what it tries to do is you tune the energy, tune the pulse and the capacitor so that the energy will transfer from one qubit to another qubit, which we won't go into detail here. Okay, so I still have 6 minutes. I want to finish it. I still have one session, but because most of you don't do hands-on, I will just show you what approximately what it is. I do want you to come up with this. Get this, understand, agree with me, right? Quantum computing has a lot of information, right? We show that you have so many basis states, but you cannot get all this coefficient. You cannot. First, even you do enough measurement, you only get the amplitude, right? So how do we use it? We use destructive and constructive interference to get some answer. For example, if the function is balanced, in Shor's algorithm, we find out what is the period of a function. Every state, if you measure a certain basis state, it corresponds to a certain period. And what period is what? The function, the period of function. It is equivalent to prime factorization. So our encryption is to find the prime factor that can multiply to the number gave to you. And it takes a very long time to find the prime factor. And people prove that it's equivalent to find the period of a function related to that number. So if you can find the period, means that how fast it repeats yourself, the output, right? I'm not asking what is F0, F1. I'm just asking when it will repeat, maybe F0 equal to F100, then its period is 100, and equal to F200, equal to F300. If I know the period, I don't need to know the function. Then I can factorize it very fast. But period finding is very time consuming. It's the same as doing prime factorization, right? So here, if we come up with smart algorithm through this destructive and constructive interference, then done. Then I get what I want. Right? So quantum computing cannot replace classical computer for sure, but it's a very powerful accelerator. Okay. Now the last session was to further to show you that how we can optimize the qubit readout using HFSS, which is a simulator. So you will see that you are just doing purely classical thing by using to help quantum computing, right? So you can look at this video. We have hands-on about 10 labs, about maybe 3 hours or 4 hours in total. Here, just want to say that I just told you the readout depends on the cross curve, how much the resonant frequency shift, right? So how do you know how much it will shift? You can do a lot of computation, but right, Dr. Milev, right, they propose a method that actually how much is shift actually depends on so-called energy participation ratio. How much energy are stored in your qubit or as the inductive energy compared to other energy, right? So these are all math, but finally it come up with that the enharmonicity and also the cross curve, how much is shift, really just depends on the so-called energy participation ratio. And energy participation ratio is just to calculate how much energy are stored as inductive energy in the Josephson junction. You can do this easily, just use classical electromagnetic field computation. And that is what it is. If you're interested, you can install HFSS, Anaconda, and Qiskit-Metal on your computer. And then with that, then you can download the example. I also post there. And of course, I copy and modify from Qiskit-Metal's website. Right? For example, okay. Okay, I did not open. So I will just quickly show you so you can follow because they're all in there. That's the last thing I will do, right? So I start Anaconda. And I also already installed Qiskit-Metal, so I will activate the environment. I call it I call it Q-Metal. No, what do I call it? I call it, Conda activate Q-Metal. Okay. Just give me one more minute. Activate Q-Metal. Right. And then I already have this. I will just go ahead to click on this. Oh, thank you. Jupyter Notebook first. Thank you. Yeah, I forgot to type Jupyter Notebook. And then now I will go there. Yeah, and then Qiskit-Metal, like it's also on the example. So what it does is that it help you to design the chip, the quantum chip, right? I run them. And then I just go through all this. And this is a quantum chip already. Remember, this is the capacitor for the transmon, and this is the superconducting qubit, right? And then you can send it for simulation. This is just, you can follow my slide. Again, if you don't have it, just email me, right? The last example is that we really can do a simulation by, sorry. Right, I also uploaded this. Okay, I just have something that already finished. Right, so these are then modified from their example. It helps you to design the chip, right? For example here, and then you will call HFSS automatically. And then you will run the electromagnetic simulation, find the modes, right? Their resonance frequency. And eventually they come up with the cross curve. And you can also add the resonator. Again, you just run the notebook, then you will be able to do that. You will send to the HFSS, right? That's all I want to say, but let me know if you have any questions. Yeah, and I like this one. In this paper, it says if you want to learn quantum mechanics is confusing, shut up and calculate will be the best method. That's why I really ask my students to do the programming. If you can do the matrix multiplication, you will understand. Okay, any questions? I will stop here.